Hello, I'm Elena, a postdoc at CPB, and in this video I'm going to present the results that we have obtained in the LiteBIRD collaboration regarding constraining a constant isotropic birefringence angle, which I will refer to as P in the following. So here's the outline of my talk. I will start talking about what is cosmic birefringence and why it is a good probe for parity-violating events. Then I'll provide an overview of the LiteBIRD mission and talk about why it's a good experiment to detect cosmic birefringence. Then going into the actual analysis, we'll describe the 4 different sets of simulations that we use and the 5 pipelines that we developed to detect beta and provide a comparisons of their performance. Then I'll wrap up with the main 2 take-home messages that I would like people to remember from this talk. So we use the term cosmic birefringence to refer to the rotation of the linear polarization plane of photons as they travel through the universe. In our standard model of electromagnetism, we expect this rotation to be 0, but there are some parity extension models that can generate this effect. In particular, we can, for example, couple the photons to an ultra-light scalar field through a Kern-Simons term. So in that case, the rotation generated would be proportional to the distance traveled by photons. So since the CMB is our oldest light that we have, it will be the best observable to test this effect. So the idea is that as the light travels and the polarization plane is rotated, it will lead to a mixing of the E and B modes, creating a non-zero EB contribution, which in lambda CDM it would be expected to be 0. The problem is that until very recently, we thought that we wouldn't be able to detect a isotropic birefringence angle because it was fully degenerate with a possible miscalibration of the polarization angles of your detectors, which I'll call alpha. The thing is, in 2020, Minami and collaborators were able to resolve this issue by basically assuming that the photons coming from foregrounds haven't had enough time to be subject to this birefringence effect. So photons coming from foregrounds will have only been rotated by alpha versus CMB photons that will have been rotated by alpha plus beta. So the best constraints that we have using this assumption comes from a joint analysis using Planck and WMAP data, and they found a beta angle of the order of 0.34 plus minus 0.09, which it would be a detection, but I think the community refrains from calling it a detection because during the analysis they needed to use some thermal dust modeling, and since we're not sure how accurate those models are, we are not calling it a detection yet. So what do we need to see whether if it is indeed a true signal or not? We need more observations. And one way that we can get new observations could be with the LiteBIRD experiment. LiteBIRD is a JAXA's L-class mission that was selected in 2019. It will measure from the Lagrangian point L2 the whole. We will provide a full survey and we will be observing for 3 years. It will have a wide frequency coverage and enough resolution to detect accurately the CMB modes. And overall, the expected sensitivity is on the order of 2.2 microkelvin per arc minute, which for comparison with other experiments is 30 times better than Planck's HFI polarization. So the main goal of LiteBIRD is actually the detection of primordial B modes. If detected, that would constitute a smoking gun for inflation. And if we don't detect it, LiteBIRD will be able to rule out many well-motivated inflationary models. Usually we characterize the power of this primordial signal using the tensor to scalar ratio, which gives an idea of the amount of power of this primordial signal compared to scalar perturbations, for example, the E mode power spectrum. Current constraints of these parameters says that it has to be lower than 0.032 at 95 confidence level, which LiteBIRD will be able to improve significantly because it is expected to have a statistical uncertainty on the order of 10 to the minus 3. So, as many of you may have heard, LiteBIRD underwent a reformation phase this last year where we tried to consolidate the mission's feasibility while maintaining the same scientific goals. The main results of this reformation study is that we have now 2 configurations that can achieve the same scientific requirements, but with a more simple configuration. Now these 2 new configurations have just one telescope with a reflective cross-dragon optics instead of the 3 telescopes that we had in the original design. And the main difference between these 2 configurations is that one has no halfway plate, unlike the original design. The second one does have a halfway plate, but with wider band, so that we can still maintain the wide frequency coverage of the original design. I'm very happy to say that in September we passed one of the key decision points that we needed to pass to move forward with this mission. So why LiteBIRD is a good experiment to detect cosmic birefringence, both the original design and these 2 new configurations? One, because it will provide very accurate measurements in polarization, and in particular for the EV angular power spectrum. Second, because it has a very wide frequency range. So we will be able to improve the foreground models. Second, we will be able to do cross checks comparing the beta angle that we recover with low frequencies and with high frequencies, because both are subject to different EV foreground modeling. It's coming from synchrotron or thermal dust. And then third, because we will have better component separation products, and actually we use component separation products for 4 out of the 5 pipelines that I will describe later. Third, we will have full sky coverage, so we will be able to recover the reionization peak that will allow us to tell apart between different dark matter and dark energy models that can explain this cosmic birefringence. Finally, even though most of this signal is larger at small scales, so high multiples, LiteBIRD has more than enough resolution to detect with high signal to noise beta angles on the order of 0.3 degrees, which is what we are currently estimating based off best constraints that we have. So now let's move into the analysis. We use 4 different sets of simulations with increasing complexity. So I will describe the phase 1 baseline case, then just highlight what we added to increase the complexity. So for the baseline case, we use for the CMB a random Gaussian realization of lambda CDM using best fit parameters from Planck. For the foregrounds, we add thermal dust and synchrotron, and we use simple SEDs, so constant spectral indices across the whole sky. In particular, we use the PySM's S0D0 models. And for the noise, we use wide isotropic noise. For phase 2, we increase the foreground complexity. So now, instead of having constant spectral indices, we have spatially varying spectral indices. We used PySM's S1D1 models. For phase 3, we include the possibility that each frequency channel might be subject to a non-zero polarization angle. So each frequency channel is rotated by a given alpha f polarization angle. And then in phase 4, we included the possibility of having a non-zero beta angle. So now the CMB map is rotated by beta plus alpha f. So here you can see a simple scheme of all the analysis. On the left you see the simulations that we used that I've just described, and on the right the 5 different pipelines that we developed. We have split them into two main groups, one where we have no control over possible polarization angles, highlighted in blue, and the other one where we can take into account that there might be non-zero polarization angles, highlighted in orange. Another way of splitting the pipelines could be regarding the type of inputs that they need. So for example, for the first two pipelines, we need a clean CMB solution. In this analysis, we've used a solution coming from FGBuster, a parametric component separation model that didn't take into account that the maps might be subject to non-zero polarization angles. For the Minami-Komatsu method, we don't need any component separation step, but we need some templates for both the synchrotron and the thermal dust emissions to estimate the EV contribution coming from foregrounds. Then from CAP-SIGRET and J23 methods, we perform a component separation step where we include in our model the possibility that each channel might be rotated by a alpha angle, and the idea is that we include priors to actually break the degeneracy between alpha and a absolute rotation bit in this case. So let me go into a little bit of more detail for each pipeline. The de-estimator is a harmonic-based method that uses a clean CMB solution, and the main assumption is that the EB comes from this mixing of E and B modes, so it's proportional to the difference between EE and BB. So the idea is that beta is estimated by minimizing this chi-square function that depends on the de-estimator. In order to take into account that this chi might be complex, for example, having more complex foregrounds, or that there might be some rotation angles, what we can do is take into account that excess power in the covariance matrix so that we obtain realistic uncertainties for beta. The pixel-based estimator is a map-based estimator that estimates beta in the following way. First, we find the extrema, so maxima, minima, in the T and E maps. Then for each extremum, its peak, we calculate the local rotation of Q and U, so the QR and UR. And what we do is stack those patterns to obtain figures like these ones over here. And the idea is that the UR for the T peaks and the UR for the E peaks are proportional to the TB and EB power spectrum respectively. So it's subject to this a non-zero signal coming from birefringence. So the idea is to fit the radial angular profile of those patterns to a model with a given beta. And the best fit would constitute our estimate of beta. The Minami-Komatsu template-based method is very similar to the one that I described during the introduction. The novelty is that it takes into account the EP foreground contribution through templates. So something that we tested in this analysis is how realistic do these templates have to be in order to get unbiased results of beta. We saw that they don't have to be perfect, so we were able to obtain unbiased results of beta using templates that were obtained using simple models, even though the sky was simulated with complex foreground. Now for CAP-SIGRET and the next method, the J23 method, both are Bayesian parametric methods that includes in their model that all the frequency channels might be subject to a rotation due to non-perfect calibration angles. The main difference is where the prior comes from. So in this case, the prior comes from the estimate from the previous method. So the Minami-Komatsu method provides estimates of the alpha parameters and also a covariance matrix with the uncertainty of those parameters. And we can use those as Gaussian priors during the component separation step to obtain a clean CMB map that, if it has additional rotation, it comes from a beta angle. So we use the estimator to obtain beta. Something that we explored in this method and not in the following is the amount of parameters that we need to fully capture the scale complexity with respect to getting a competitive uncertainty of beta. Because if our parameters is too big, maybe we have an unbiased value of beta, but we have a non-detection of a similar detection to what current methods are obtaining. So we found a sweet spot between the amount of foreground parameters that we needed and the getting an unbiased beta value with competitive uncertainty. This for the J23 method. The difference with the previous one is now that the priors come from experimental constraints. So from calibration sources, polarized sources like tau A, or from lab specifications, or from other calibration sources. The idea is then later from the clean CMB map beta sets estimated by sampling this cosmological likelihood. And another difference with respect to the other one is that instead of exploring what is the amount of foreground parameters that we need, is use simple SEDs to model the foreground, so constant spectral indices, but we will mask, we will do aggressive masking to avoid the need to increase the parameter space. And we found that doing this, circumventing the foreground complexity by masking, we were still able to obtain unbiased results of beta with competitive uncertainty. So here is a comparison of all pipelines for the 4 different sets of simulations, 5 different pipelines. So you can see all of them provide good results in all cases, and the best results were obtained with the template-based extension of the Minami-Komatsu estimator. And for that one, we have found that we can detect a beta angle of the order of 0.3 degrees with more than 10 sigma. So I just want to finish now by saying, with these 2 main conclusions. First, LiteBIRD will be able to confirm or reject the hints we've seen of beta because of 2 main things. Because it has a wide frequency coverage that will allow us to produce better models for the foregrounds, in particular the thermal dust, because it has a full sky coverage and will allow us to test different models for this EV signal. And second, we have developed 5 different robust pipelines that can tackle 2 of the main problems when it comes to the detection of beta: foreground complexity and polarization angles. So thank you for listening, and if you have questions, please feel free to ask me in the asynchronous discussions or in the live discussions. Thank you very much.